All right, so this is part two of the types of reactions. We're going to look at single displacement reactions first. So a single metal or nonmetal combines with a molecule and knocks out its partner to recombine. And that's what we call a single displacement reaction. So what that looks like is we get the metal displaces the nonmetal, or sorry, the metal displaces the metal in the compound and takes its place. So for this example, copper metal reacts with silver nitrate. The copper is more reactive than the silver, so it pushes it out of there, takes its place with the nitrate ions, and we are left with silver metal on its own, and the copper is part of the compound now. So what replaces what? Well, the copper replaces the silver. Of course, we have to balance this. So in this case, we need 2's in front of the silver nitrate and a 2 in front of the silver. We need to remember too with single displacement reactions that anions can be displaced as well. So for example, fluorine can displace the bromine in potassium bromide. We're left with bromine and potassium fluoride. In this example, magnesium with hydrochloric acid, magnesium displaces the hydrogen, make magnesium chloride, leaving just hydrogen. Why is it a single displacement reaction? Well, metal is displacing hydrogen, which acts as the cation, right? So if we balance this, we end up with a 2 in front of the HCl. Now, the question, of course, then is what determines whether a single ion displaces another in a reaction? For that, we have to use the activity series in our periodic table. We use the activity series of metals, and it gives us a list of the various metals in order of reactivity. So you need to have this beside you as a tool. You will be allowed to use this for all tests and so on and so forth. So make sure that you have it with you. If the lone metal is higher in activity series than the one in the compound, it'll be able to displace the metal in the compound and take its place. If not, you don't get a reaction. Nothing happens. So here are some questions from the textbook. Give those a try. They're all fairly straightforward. Double displacement reactions are reactions where you have a compound reacting with a compound and the cations switch places with the anions. How do you know a chemical reaction takes place? Well, you're looking for signs. What is it that you see, smell, hear, that sort of thing? The first one is that if you see a solid precipitate forming where everything was in solution before, that's a pretty good sign that something happened, that a reaction took place. Secondly, if water is one of the products. Now this one is a little more difficult because quite often we're dealing with solutions which are in an aqueous environment. And in that situation, then you have, if water is being formed, it is really hard to tell, and you quite often need a secondary way of figuring out whether the water has actually appeared or reacted there. Thirdly, you would see bubbles, like carbon dioxide or ammonia gas are given off. That's a definite sign that there's a reaction. So let's take a look at some examples. Lead nitrate reacting with potassium iodide. This chemical reaction produces these two ionic compounds. What happens is that the cation from the lead and the cation from the lead nitrate and the cation from the potassium iodide are really just switching places. The lead goes with the iodine, and then the nitrate goes with the potassium. So in order to figure out if this reaction is actually going to happen and if these two things will actually form, then we have to use what we call our solubility rules. And that's the bottom table on the back of your periodic tables. Solubility rules are listed in hierarchy. So there's the rows from 1 to 6, and 1 always takes precedence over 2, which takes precedence over 3, and so on all the way down the list. So the way we do this is we look at whether or not one of these ions in the compound are soluble or not. If it's soluble, that's not necessarily meaning that it's going to react. It's just going to stay floating around in the water. If it's insoluble, it'll come out of solution. And so what we do then is take a look at the compound and how these ions kind of fit from this table, what the table tells us. If it turns out that both ions are soluble, that is, they dissolve in water, then you're going to get no reaction. One of them at least has to be, one of the combinations has to give you an insoluble product. Only then will you get a chemical reaction. So, for example, let's look at calcium chloride reacting with aluminum sulfate. All right, so the possible products that we could get are calcium sulfate and aluminum chloride. So on a separate sheet of paper, you would write down just that without any kind of subscripts. So pretend the solid and the aqueous aren't there. If that's the case, then we go to our solubility rules and we look at calcium and we look at sulfate. Calcium, we notice, is on the sixth one down. No, sorry, fifth one down. And it's a metal. Okay. And it is found to be insoluble. Sulfate is on the one below that, which means it's not as high a priority, but it's soluble. And so we have the calcium taking precedence over the sulfate, and so therefore the compound therefore is going to be insoluble. Looking at aluminum and chlorine, aluminum again is down on the fifth, and it's insoluble. But the chloride is on the third level, and it's soluble, so it takes precedence, and so this compound is going to be soluble. And so it becomes an aqueous solution. So as long as one of our products is going to be insoluble, we get a reaction. So in this particular case here, calcium sulfate gives us an insoluble product, and therefore the reaction goes. And of course we balance it. Let's try this example. So ammonium nitrate and barium chloride. All right, so double displacement, we would get ammonium chloride. And if we look at the solubility rules for those two ions, ammonium ion is in the first row, it's soluble. Chloride ion, again, is in the third row, it's also soluble. So two solubles make soluble, and therefore this is going to be a soluble product. It's going to stay aqueous. The barium with the nitrate ion, barium is in the second row, it's insoluble. The nitrate is in the first row, and it takes precedence, and it's soluble. So that means we're going to get two products that are both soluble, which means that all the ions stay in solution and nothing is going to form. We're going to get no reaction. So we put down NR. So now there are two products that if we see them, we're going to have to think, oh wait, that one's one of those special cases. And it decomposes in the presence of water. And it forms water and some sort of a gaseous product. The first one is carbonic acid. If we look at follow the solubility rules, then carbonic acid should be soluble, and it is. However, in the process of dissolving in water, it actually reacts with the water molecules, and the water molecules decompose it to give you carbon dioxide and water, more water. So as a result, you're going to get some bubbles, and you're going to see something actually happening. The second one is ammonium hydroxide. It's a similar type of decomposition where ammonia gas is given off as well as water molecules. So if you see carbonic acid or ammonium hydroxide as one of the products in a double displacement reaction, then you've got to think, oh, wait a minute, that's one that decomposes. I got to remember that. It's not going to give us a no reaction, it's going to give us a reaction here. So try these as your homework and ask questions if you have any. Later on in the solutions unit, we'll talk more about acid-base reactions, but acid-base reactions are a special kind of double displacement reaction. When you have an acid reacting with a base, they neutralize each other. And this is where that second category comes into play, where we form water molecules as part of our products. Now, the water is kind of hard to spot, and so we use indicators to kind of tell us where and when it's been neutralized. But otherwise, you really can't see much happening with these types of reactions. They're a bit boring. So an example of an acid-base reaction is hydrobromic acid reacting with sodium hydroxide and HBr plus NaOH. The salt that's produced is the sodium bromide. It's still soluble in water usually, and then water is the other, and this is the liquid state. So let's practice some of these. All right, so here's a bunch of reactions. Take some time, pause the video now, and have a look and try some of these. Okay, now that you've had a chance to try them, the reactions are as follows, and this is what you should get. So the first one is a reaction where barium sulfate is the solid precipitate. Balancing that, it's already balanced. We really should write balanced here. The calcium hydroxide with the ammonium chloride. Ammonium chloride is going to give us ammonium hydroxide. The ammonium hydroxide breaks down into the ammonia and water, so you got to remember that. Third one's a combustion reaction to give us carbon dioxide and water. The fourth one here is a decomposition reaction, but this one you could, I guess, go Pb plus O2, but Pb is the more oxidized form, and so it usually goes stepwise to the less oxidized form first, form PbO plus O2. If you decompose PbO, then you would get Pb plus O2. The double displacement reaction between calcium hydroxide and aluminum sulfate. It's a unique situation actually where both products are solids, and that's fine. It can happen. It doesn't usually, but in this case it does. But we still get a precipitate, so there's definitely a reaction. The sodium metal plus water, so this gives us the hydroxide and hydrogen gas. And then iron and oxygen is a synthesis reaction giving us iron 3 oxide. But because iron can form 2 possible oxides, how do you know which one will be preferred? Look at your periodic table. I've listed the oxidation numbers in order of, I guess, most common one first. And so the 3 plus is over the 2 plus, and so you'll write down iron 3 oxide. And that's it for those reactions.